So hello, and welcome to problem 43C, where we will be comparing the tail of the Weibull distribution against the tail of the log-normal distribution. And I can see I just forgot to write down the log-normal density here, so let me just write that down. So the density of the log-normal distribution with parameters mu and sigma squared evaluated in x is equal to 1 over the square root 2 pi multiplied by 1 over sigma multiplied by 1 over x multiplied by e to the minus 1 over 2 sigma squared multiplied by log x minus mu squared. And what we kind of just notice here as well is that we assume mu to be just any real number, and we assume a, b, and sigma squared to be greater than 0, just so that we know which cases we should cover when we take a look at this. So let's try to just go forward as we have done before, where we consider the ratio between the two densities, and I will call the ratio h of x. So consider the ratio of the densities h of x. So consider the ratio. Densities h of x, which I will define as such. Oh wow, I should really move this down a little bit. There we go. Which we will define as such. It is, well, I choose to put the Weibull density in the numerator and the log-normal density in the denominator. So what I will be able to conclude when I take the limit of this ratio for x going to infinity is if this ratio goes towards infinity, then the Weibull has the heavier tail, and if it goes towards 0, then the log-normal distribution has the heavier tail. So this ratio of densities is proportional to the Weibull density, where I remove all the constants that have nothing to do with x, divided by the log-normal density, where I remove all the constants that have nothing to do with x. And what we can kind of see here is I divide by 1 over x, so that's the same as just multiplying by x. And down here I have e to the minus 1 divided by 2 sigma squared multiplied by log x minus mu. Then take this and square it. Okay, so again we notice that I have two exponential expressions, so the smarter way to do this would be to take the logarithm of the ratio and consider the limit of that instead. So I take the logarithm of the ratio, and as before I notice that I just have to add a constant k representing the logarithm of the ratio between the constants that I threw out, and then I add the log of all of this. So first of all, I just kind of note that x to the b minus 1 multiplied by x is just the same as x to the b, right? So I have log of x to the b, which is b multiplied by log x. And then I have log of this, which is just minus x over a to the b. And I have minus log of this thing down here, and I have minus minus, which gives me a plus, so plus 1 over 2 sigma squared multiplied by log of x minus mu squared. Okay, so what can I conclude here? Well, it's not as easy as the earlier cases, and the reason why it's not that easy is, well, quite quickly we kind of notice that log x will probably be eaten by one of the other terms, but what is the most dominant term, x to the b or log x squared? Because if this one is the dominant term, then the log ratio will converge towards infinity, right? However, if this one is the dominant term, it will go towards minus infinity. So what I really need to find out right now is it this or this that that grows quicker towards infinity as x goes towards infinity. And how do I do that? Well, the way that I can do that is I can take a look at the ratio between these two. So what I want to ask is, does x over a to the b or log x minus mu squared go quicker? Or actually I also have the 1 over 2 sigma squared here, go quicker towards infinity as x grows towards infinity. Because if this one is the one that grows quicker towards infinity, then my limit here for x going towards infinity is minus infinity. However, if this one grows quicker, then my limit is plus infinity, right? So I need to figure out which one of these goes quicker towards infinity. And one way to do that is to look at the ratio of x divided by a to the b over 1 over 2 sigma squared multiplied by log x minus mu squared, right? Because if this ratio goes towards 0, then that means the denominator tends towards infinity quicker. If this ratio goes towards infinity, it means the numerator tends towards infinity quicker. So what does this go towards? Well, the limit of this for x going towards infinity, let's take a look at the numerator. Well, this goes towards infinity, and this goes towards infinity as well. So what we can do is we can use L'Hopital. So here I'll just write L'Hopital. And the limit of this ratio is then equal to the limit of the ratio of their respective derivatives. And what I see here is the derivative of this thing here is roughly something that is x to the b minus 1, right? So what I have here is actually it is b multiplied by x over a to the b minus 1. And what I have down here is, well, the constant is still there, and then I have the derivative of my outer function, which is 2 times the 2 times the inner function multiplied by 2 times the inner function to the first. So that is, this is going really well, 2 times the inner function to the first. Well, that's just a 2 up here and log x minus mu. Great, and then I differentiate the inner function log x minus mu, which just is the same as 1 over x, right? So I divide by 1 over x in the denominator, and that just corresponds to multiplying by x up here. So what I see is that I then get the ratio between, the limit for x going to infinity of the ratio of b multiplied by x to the b divided by a to the b minus to a to the b. So I just forgot to mention that probably earlier here. This should be x to the b minus 1 divided by a to the b. Yes. And then down below we have 1 over sigma squared multiplied by log x minus mu. And quite clearly, this is equal to infinity, since we know that x to any positive power grows quicker to infinity than log of x. So this ratio is infinity, and because this ratio is infinity, we know that this term is the one that goes quicker towards infinity. So we can write hence x over a to the b goes towards infinity quicker than log x minus mu squared. Hence, the logarithm of h of x will be dominated by this term for x going to infinity, and it will then converge towards minus infinity as x goes to infinity, which in turn tells us that that means that the log normal distribution has the heaviest tail. So hence, the log normal distribution has the heaviest tail.